Welcome to homework.
Hi everyone, so what we have today is a problem that is dealing with equilibrium and elasticity. So what we have is a flood lamp that's hanging from the end of a vertical steel wire, and under the weight of the flood lamp and after reaching equilibrium we see the wire stretches a distance of 0.18 millimeters, and we know that stress is proportional to strain. We are asked to solve for the new change in length if the original length is if the length now is 2 times the original length. We're also asked to solve for the change in length if the new diameter is 2 times the original diameter, and then if the material is changed to copper. And the way that we're going to be doing this is by using our knowledge of proportions, forces over area that are equal to stress, and then also the stress-strain equation relation. So let's go ahead and get started. So we'll do the first question where we're asked to solve for the change in length if L prime is now equal to 2 times L. We're going to know that sigma, which is our force over area, is going to be the same as the original case. Therefore, we know that the strain is going to be equal to delta L prime over L prime. And these are, L prime indicates our new quantities. Now we know that the strain is going to be the same as the original case because sigma is proportional to strain, and sigma is our stress. Now we have force over area. The area of our wire is not changing. The force is not changing. Therefore, sigma doesn't change. Therefore, our strain does not change as well. So by using this relation shown here, we can solve for delta L prime, and we see that delta L prime is equal to the original strain times L prime. Now if we're plugging in for L prime, we know L prime is just going to be 2 times the original L, and the strain is just L, or delta L over L prime. So this is actually just equal to delta L over L times L prime. So we know that L prime over L is equal to 2, and delta L is 0.18 millimeters, so this gives us a delta L prime that's equal to 0.36 millimeters. And that's the answer to the first part of our question. Next, we're looking at the case if the new diameter d prime is equal to 2 times the original diameter. Then we know that sigma is going to be changing because sigma is equal to force over area. And this is a definition. So we can then say that sigma prime is going to be equal to force over our new area, which is just pi d squared, because that is just pi d prime squared, but we know that d prime is equal to 2 times d. And our original sigma is just going to be f over pi d squared over 4, because we just have one diameter. Therefore, we can see that sigma prime is equal to the original sigma over 4. Since we know that sigma is proportional to strain, we now know that with our sigma prime, this is going to be proportional to our new strain prime. And by this, we know that the strain prime is just going to be the original strain divided by 4, which is equal to 0.45 millimeters. That's the second part of our answer, and I'm just going to multiply this by L to give us our new delta L prime. So I'll multiply this by L as well. Next, we have our last case when we're using copper instead of steel. So now this is just going to be the ratio. It's going to involve the ratio of our Young's moduluses for these two materials. So we know copper has an E, or Young's modulus, that's equal to 117 gigapascals, and steel has a Young's modulus that's equal to 215 gigapascals. Therefore, the strain is just going to be using ratios between these Young's moduli and multiplying that with our original strain. So we can say that E prime will be equal to the Young's modulus of steel over the Young's modulus of copper times the original strain. Then we can say that delta L prime would just be equal to L times the strain times this ratio between Young's moduli. Plugging in for these values gives us that delta L prime is equal to 0.33 meters. And that's our final answer.